So for a long time in robotics, it had been the case that you would get your hands on a robot, and then you would write a whole bunch of what we would call infrastructure, software to go with it. And that was just to make the robot vaguely work. Then after that, you could do what you actually wanted to do, which was to do an experiment, solve a problem, test a hypothesis. And the goal with ROS was to make it so that we took care of all that.
November 7, 2007 in Menlo Park, California, an engineer at a Silicon Valley robotics lab called Willow Garage published an open source repository on SourceForge.net. The repository was called ROS Code, and this was officially the first time the term ROS or Robot Operating System was officially used within the robotics community. Fast forward to this day, ROS is considered the de facto standard for robot programming, and it is used in a lot of different domains and applications ranging from agriculture and food delivery to logistic to service industry and even autonomous driving. A lot of different startups, Fortune 500 companies, academic research labs, and even government agencies have started to adopt robot operating systems for their projects. But the question to answer is that why is this the case? Why do we even need ROS? And to understand this and to answer this question, first of all, we need to understand the complexity of a robotics system. A typical robotic system consists of a lot of different components and modules and sub-modules, and this makes the overall development and implementation process for a robotics program so that it can achieve a specific task or a goal really difficult, because a lot of different components need to be implemented. So these modules could be behavior or task planning modules, these could be motion planning and navigation modules, these could be controls, the control architecture needs to be implemented, the actuators and sensors need to be taken care of, there are perception modules, there might be a need to define the world model. So all of these things necessitate the need to define and implement sensor drivers, actuator drivers, internal and external communication modules, control architecture, and behaviors. So all of these things are a lot to be implemented by a single person or even a research team focusing on a particular aspect of robotics. So a particular researcher would have a certain interest. Let's say he is an expert within the sensor domain, so he can probably implement the sensor drivers really well because he understands it really well, but he might also need to implement the actuator drivers and also the internal and external communication modules and other components that are needed within robotics, because without the other components these things would not work. Now you might say, hey, these are things that could be used easily from other research institutes or other people who might have contributed to it, and this is exactly what was missing in the early days of robotics research, and hence researchers unfortunately had to implement these things by themselves and mostly from scratch. And this was incredibly overwhelming because not every researcher is an expert in every domain of robotics, and it is impossible to master all of the domains within robotics for a single person. So there are teams and teams of people working in different domains and subdomains within robotics, and it was really overwhelming, and this really was a hindrance to making progress within robotics research for a really long time. Essentially, the researchers were reinventing the wheel. The same sensor drivers and modules were being implemented again and again within different robotics research labs and companies because they had no other way, because they didn't have access to sensor drivers that were probably being developed by other companies or research institutes. Now you might be wondering, hey, why is it the case? PhD students would often spend 3 years on just writing the software of the code, and they would spend 90% of their time rewriting the code, and only 10% of their efforts were spent on innovation. And why is it the case? Let's have a look at a typical robotics research scenario that used to take place within the early days of during the early days of robotics research. So a research lab would publish an interesting research, a paper with a proof of concept for a novel robotics algorithm or a concept for a robotic system, and this would generally capture the interest of capture the interest and attention of another research lab who would want to build on top of this research. And this is how research works. Someone publishes a research paper, and then other research institutes would build on top of it, and this is a very collaborative effort. And this was how the case was, and the research lab would then want to use their code from scratch, but the code that the original paper might have published might not be that easy to implement and might not be very well documented or created, because as I mentioned, the researchers who were publishing these codes had to implement a lot of these modules and components from scratch again, because they had no other way to deal with that. So this is why the code that was created was not of the highest quality. So they couldn't get a lot of details on the software used to make it work, and the code used by the previous lab would essentially not be reproducible or easily reusable. And essentially they would have to resort to really writing the code from scratch, and eventually time would run out and they would have to publish the paper with the code, and the cycle continued. So all of these contributed to a lot of incomplete or non-reusable code that was not very useful for the robotics domain, and the researchers were essentially recreating the same sensor and actuation and communication modules over and over again. So there needed to be a solution to this problem, because this was just a waste of time for the researchers who should be spending their time really generating novel ideas and testing and conducting experiments on novel algorithms instead of re-implementing the same things over and over again. The researchers would spend their time building required hardware and rewriting the software, leaving them with little to no time on new research. And there needed to be a revolution. A revolution needed to happen similar to the revolution that happened within personal computers. Within personal computers, there's a well-defined set of applications that are generally used, and these applications are built on top of an operating system. There's a specific common system software that is used in even a lot of different operating systems. So there's a common ground on what is the architecture or what is the sort of framework or the overall concept of system software that needs to be used. Likewise for hardware, even though there might be different kinds of computers, the underlying hardware, the keyboard, mouse, the overall concept is essentially more or less standard and common. And this is the kind of revolution that needed to happen within robotics as well, within personal robotics. So within personal robotics, the applications could still be explored, and that might have needed more time. But even before exploration of these applications, the system software and the hardware needed to be standardized. So this was an urgent need if we even wanted to make any progress within robotics. If there was to be any progress within robotics, these were the two major components that were missing. There was a need for a standard robot software framework and a common robotics platform. In 2006, two researchers from Stanford University decided that they've had enough. There was enough time wasted within robotics that could have been spent towards meaningful research, and they managed to get a funding of $50,000, which was not really that enough, but they decided to start a personal robotics program within Stanford University. So these two researchers or PhD students who were called Eric Berger and Keenan Weirebach decided that they would actually take this problem into their hands and take responsibility for finding a solution. And they decided that we want to build a framework that allowed processes to communicate with one another and create code and tools on top of that. So this was a significant step that contributed towards the starting or the beginning of a revolution within robotics, because no such framework already existed. And essentially, they started with creating a personal common hardware. They managed to create a personal common robotics hardware, and they called it PR1 with the limited funding that they got. However, since the funding was limited, they could not continue researching on the hardware, and also the robot software framework was not really developed at that point. So there needed to be more funding. They needed to get more funding, and this is what they exactly did. They pitched their ideas to a lot of investors, and finally in 2008 they managed to meet the founder of Willow Garage, Scott Hassan, and Scott Hassan actually was quite impressed with the ideas that Eric Berger and Keenan pitched to him, and he was so impressed that he decided to incorporate their personal robotics program within Willow Garage itself, and really give them the freedom to continue progressing this idea. And Scott Hassan and Eric and Keenan were aligned on a lot of different ideas. They wanted to make progress within robotics. They had similar ideologies and viewpoints, and so all of these things fell into place with their collaboration with Willow Garage. And so with this, Eric Berger and Keenan with Scott Hassan started the development of PR, the personal robot, and the robotic software framework. So one of the goals with PR2, which was a subsequent version of PR1, the personal robot, it was to support the next 5 years of software development. So the goal with building the hardware was to have a common software platform. And this is what happened with the support of Willow Garage, and with the funding and the personal robotics program being incorporated within Willow Garage. The personal robot along with the robot software framework finally came into being. So we had a PR2 robot, personal robot platform, and also a robot software framework. And this is where ROS was finally born. So this started the revolution of having a common robot operating system, a common robot framework that could be used in industries and research. So just like with personal computers, we had applications, system software, operating systems, and a common hardware. Within personal robotics, we started to get a common software framework, which is robot operating system. It is not exactly the same as a computer operating system, but this is why ROS is called robot operating system, because it emerged from this analogy of operating system within the software domain as it applies to personal computers. And for hardware, they managed to create PR2.
So we're gathered here to celebrate the launch of the PR2 and the PR2 beta program.
Introducing PR2. PR2 is a robot designed from the ground up to enable software developers to focus on new ideas and new technologies. Capable arms, powerful onboard computing platform, sensors in the head, body, and even cameras in the forearm, and of course, it runs ROS.
Our vision for ROS is for it to become the Linux of robotics, a free, open source platform for people to build on.
And this was followed by delivering 11 of the PR2 robots to 11 research centers and allowing them to really work on using ROS and PR2 for advancing research. So this was the first step towards really making advancements towards the personal robotics vision that Eric and Keenan had from the very beginning. And so robot operating systems started to be used, and with this, the first version of ROS was officially released in 2010. 2010, ROS 1.0 was released, and this was followed by the first official version of ROS, which is ROS Box Turtle, in 2010 itself. And this just started the release of ROS, and fast forward to this day, we know that there's a lot of different ROS versions that are available, and ROS is being constantly developed and it is being maintained by Open Robotics currently. So ROS 1 was released and Box Turtle was released in 2010, and then different versions of ROS, Groovy Galapagos, Indigo Igloo, and a lot of different ROS versions, ROS Melodic, ROS Noetic, were released in 2018 and 2020 respectively. And then also in December 2017, ROS 2 started being developed actively. So now if you notice this, if you look at this diagram clearly, you'd be able to find a common ground or a common point for all of these different ROS versions. And if you look closely, you'll be able to see that all of these ROS versions essentially have use the theme turtle. And you might be wondering, hey, why is this the case? Why do they have a turtle or a specific species of turtle within their name, and why do they have the turtle theme? And this is an interesting thing to really contemplate on, and I would like to share with you a clip from a podcast on the YouTube channel The Construct, and they have really elaborated it and mentioned it in a lot of detail. So on the Construct channel, there's an interview with Tuli Futer, and this is what he mentions. He is the ROS platform manager at Open Robotics, and he is responsible for essentially naming all of these ROS frameworks. And Ricardo Telles from ROS Construct, he asks him, hey, why do you name these ROS versions with turtles? Why do you have to use the turtle theme? And this is an interesting response from him. So let's have a look at this.
Why are you putting those names of turtles to the ROS distros, and how do you choose the names?
There's no hard and fast rules about what the names are. We do have a turtle theme, but we've had things like Indigo Igloo, which is not a turtle, but it sounds cool. So,
okay. But why turtles?
So I believe Box Turtle was picked before we had a theme, but we liked the turtle because it has a lot of creation myths and turtles all the way down. And as we were getting ready for the release that became known as Sea Turtle, one of the things that we were working on is that we realized that we had our like full robotic simulators, but we actually needed a turtle, like a simplified simulator to teach people ROS in the tutorials. That's even simpler than our simplest robot. And from that, Turtle Sim was born because a bunch of us grew up and used Logo.
Yeah.
And we remembered that Logo, the little cursor in Logo, is called a turtle.
Yes.
So from Box Turtle in 2010, each ROS distribution has been named after a different turtle species, and since 2015, each release has taken place on World Turtle Day. So if you have noticed, since 2015, all of the ROS versions have been released on the same date, 23rd May, and that is the World Turtle Day. And now you know why all of the ROS versions are named after turtle species. So to summarize, let's have a look at how the development of ROS took place. So in 2006, Stanford Personal Robotics Program began building the PR1 robot with Eric Berger and Keenan Weirobek. And then Willow Garage hired its first employees in January 2007, and the first PR1 prototype is announced. In 2007 November, Willow Garage begins its personal robotics project and formalizes ROS with PR2 released. And then ROS.org is officially created in August 2009, and ROS 1.0 is released in 2010. Willow Garage gifts PR2 robots to 11 research institutes to continue researching on different algorithms and approaches within robotics and developing interesting systems. And in 2010, Turtlebot is created. 2011, ROS reaches 100 repositories. And in 2013, ROS moves to open robotics. So ROS was officially starting to be maintained by Open Robotics, and Willow Garage officially shut down in 2014. And in 2017, as we saw, ROS 2.0 is released, which is now starting to be used more rapidly within the research institutes and industries. So now, looking at all of this history of ROS and looking at its origins and connections with turtles and all of these interesting things, and how robotics research used to struggle and how ROS solves a lot of these problems within research, you might be wondering, hey, why did I spend so much time really explaining and digging into this one idea of why do we actually need ROS and talking about the history of ROS instead of really making a tutorial on using ROS for a certain project, which is what I would probably also do in the future in the coming videos. But the reason why I start this video, or I created this video explaining in detail on why do we actually need ROS, is because if you understand the importance of ROS, you would be taking it seriously and you would be spending time really building those skills within ROS. And one of the core reasons why you should spend time learning ROS is because it is being used everywhere now. ROS and ROS 2 specifically is being adopted by industries and research institutes, and it is mentioned in a lot and most of the job profiles that are titled robotics software engineer. So this is the main reason why you should be learning ROS. But you might be wondering, hey, why is ROS being adopted so widely? And now you know exactly why. So now that you know why you should know ROS and why ROS is being used in the industry and research, how do you start learning ROS? The best way to learn ROS is by building projects, and I've created a detailed video titled ROS Projects for Beginners, where I give you a list of 10 beginner-friendly ROS projects, so go ahead and check that out. And I've also given a complete list of ROS 2 resources. These are also beginner-friendly resources, so also go ahead and watch that video. These are really detailed, comprehensive videos, and these should give you enough understanding of the basics of ROS and which resources to look for, what kind of projects to start building, and what should be the official process to really learn ROS. And lastly, I'd like to mention that I have created a couple of courses on my website, learnroboticsandai.com. I've created a free AI generated OpenCV crash course, which is a AI moderated, AI generated and storyline driven interesting way of learning OpenCV. Currently only the first chapter is launched officially on the website in this course, but if this is something that you find interesting, you can go ahead and also fill a form by the end of the first chapter modules. And if there's enough interest, I would continue building the subsequent chapters, because this requires a lot of effort. And secondly, I've also created a more detailed, comprehensive course called Become a Self-Taught Robotics Software Engineer. This is something that you can find on the website learnroboticsandai.com/challenges. learnroboticsandai.com/challenges. So go ahead and check that out. This is a more step-by-step guide. I also offer you a community that you can interact with and find accountability partners, and really a step-by-step module-driven framework to become a self-taught robotics software engineer. Go ahead and check that out if this is something that you find interesting. So finally, thanks a lot for watching this video. Stay tuned and subscribe to Learn Robotics and AI, because I'll be making more ROS related projects, ROS related videos in the future. And make sure to mention in the comments what kind of videos you would like to see in the future, because this is something that I would then spend some time researching and creating a really long form videos. And also, do you like long form videos, or do you want me to make shorter videos as well?